Okay, so I am going to go over the problems from last year's, or not last year's, from the old final exam that your professor posted, and just wanted to let y'all know that these problems they are challenging. You know, I they were harder than I was expecting, so you'll want to make sure that you go over all your old work, your old homework and everything. Make sure you know how to do everything. Um, so this first one, we have a capacitor and we have switch action. So this is a topic, from your last test, but you obviously have to remember everything, from previously as well. And so the first thing says to find the energy stored in the capacitor at t equals 0 minus. So I had mentioned in the review for the last test that one thing you will always have to do with these problems is to look at the circuit at 0 minus and see what it looks like and see the conditions at 0 minus. And so at 0 minus, you will assume that the switch had been closed for a long time and that under DC, a capacitor acts like an open circuit. So for 0 minus, so I'm going to draw t equals 0 minus, what the circuit looks like. And if while you are watching this, or um, if you are here, uh, you have any questions about why I chose to use a particular method for doing something, just ask, because there's always multiple ways of doing things, and if you do it right, then we should get the same answer no matter how you do it. Um, there are also wrong ways of doing things as well. So if we look at the circuit the way I drew it at 0 minus, the capacitor acts as an open circuit. So we are going to need to get the voltage across that. But what I'm going to do right now is to actually erase it so that we can see, just have a better picture as to what this circuit looks like. So it looks, so there it is, and we are trying to get the voltage from here to here. Uh, well, I am trying to get that voltage because we need to get the energy stored in the capacitor at time t equals 0. And so the energy is 1/2 CV squared. So that is the energy stored in a capacitor. So we have to have the voltage across that capacitor, and so that's why I said I wanted to measure that voltage. Now, this circuit, if we look at it, it's the way it's set up right now is kind of strange, but we can make it look a little more normal if we consider that we've got this loop right here that's got our voltage source and a resistor. And then we have um, another branch here that's connected here and connected here. So it's connected at this point and at this point, and it has two resistors in series on it. It's got a 10 kilo ohm resistor and another 10 kilo ohm resistor. So to start off with, I'm just going to combine those into one 20 kilo ohm resistor. And so I just took this outside loop and made that one 20 kilo ohm resistor. And now when you look at it, did I draw this one right? bias. We can see, and this one was a 10 kilo ohm resistor, no, a 5 kilo ohm resistor. Actually, I don't think, I think I wanted to save that. I'm going to do that one when I look at it at greater than 0. So I don't think I actually need to do that right now. I may come back to it. So right here, if I look at the circuit as drawn here, this was a 10 volt voltage source. If I make this ground, then I am at 10 volts right here. And the thing that is strange about this circuit is this is ground, and so everything here has to be at 0 volts. So this is at 0 volts, and this is at 0 volts right here. And so if I tried to see if there was any current going between, say, point A and point B, then I would say that my current equals VA minus VB over the resistance in between them, which is 20 kilo ohms. But that would be 0 minus 0 over 20 kilo ohms. And so there is no current flowing on this branch. And so I've got 0 volts here, 0 volts here, and there's no current flowing, so I also have 0 volts here. And so my voltage difference from one side of the capacitor to the other is 10 volts. So VC at 0 minus is 10 volts. So at 0 minus, the same thing, you can see the same thing here on the way that I drew the circuit here. It still is true that if I make this ground, and this is 10 volts, and this is 10 volts right here, all of that energy gets dissipated across the 5 kilo ohm resistor because I get back to 0 volts over here. So again, there's no current flowing through that outer loop. So at 0 minus, my energy equals 1/2 times my capacitance, which is 100 nanofarads, so 100 times 10 to the negative 9, times my voltage squared, which was 10 volts squared. That's U equals 1/2 CV squared, or 1/2 times 10 to the second times 10 to the negative 9 times 10 to the second, which is 0.5 times 10 to the negative 5, which is 5 times 10 to the negative 6, which is 5 microjoules. So that is the answer to part A, finding the energy at time t equals 0 minus. So are there any questions on that part?
Would you also say that when t is in parallel with the 5K?
No, it's not, and that's why it's kind of weird, because it's not in parallel with the 5K. It's actually, and this is another way to show that there's 0 current flowing through it. It's actually in parallel with a short. Let me show you why. So if I look at, this is what I was about to do, and then when I went back to the original circuit, I look at, it's got the 20 kilo ohm resistor is connected right here and right here. And so it's, if I think about taking this resistor in 3 dimensions and picking it up out of the page and folding it over, it would look like this. So I've got this part already, but then I'm folding this part over, like picking it up and folding it over, and so it looks like this. And now you can see that it is in parallel with the straight wire. It is in parallel with the short. And that means that no current is ever going to flow through it. All of the current is going to flow through the short. And things are in parallel if they're connected at their ends, if their ends are at the same voltage, and that's what we've got here. This end is at 0 volts and this end is at 0 volts, so it's in parallel with that. Did that make sense?
Yeah.
Okay. So not in parallel with the 5 kilo ohm resistor, but in parallel with the short. Okay. Now we are supposed to find IR of 0 plus. Now, in our original circuit, IR is in this direction. So at 0 plus, we need to redraw our circuit the way it looks at time 0 plus. And let me grab it. Okay, so at 0 plus, I will have opened up that switch, and so now it will look like this. I've got my capacitor no longer an open circuit, and it's IR that I'm looking for right there. And this part is now open, and I have that. And I just was showing with the zeros, this is T equals 0 plus. Like I was just showing with the circuit up above, if you think about taking this part right here and just picking it up out of the page and folding it over, notice it's connected to the rest of the circuit here and here, and so we can draw this. It's in parallel with this side, so it's let's see. Right there. So it's in parallel. Oh, hey, I was down there earlier, like at y'all weren't there at like right at 6 o'clock, right?
We were. I came at like 5:30, and I sat at the door.
Oh, but I said I'd be there at 5:55.
Yeah, but I thought I would meet you when you came, so I just.
Okay, I was down there at 5 from 5:50 to 6.
That's crazy. We were.
Were y'all outside? I was just inside the door, like where I must not.
Cause the door was locked, so we couldn't get in.
Right, but I thought I would see you like right outside the door, but.
Wow.
I'm so sorry.
No, you're fine.
Okay, I'm very sorry. I did not. I was not. I did go and look for people. I promise. Okay. I should have sent out that email. Darn it. I don't know. You might not have seen it. I was going to send out an email saying, "I'm just checking. Is anybody here?" I do have now 3 people on Zoom, but
Okay.
yeah. Okay. Let me turn the projector back on. Yeah. Okay, so I'm gonna, and then I know that a couple of my Zoom people came in late, so I'm gonna do just a quick recap of where we are on this first problem. So I started off by saying, I'm going over the old final that he posted, and just want to say that I found it harder than the other stuff has been. So just want to give y'all a heads up on that to make sure that you study for it a lot. And so this first problem has a capacitor that has a switch that opens at time t equals 0. And one of the things that's kind of interesting about this capacitor is the geometry of the circuit is different. And so at t equals 0 minus, when I make the capacitor open, so I've got, here's my capacitor is open and it's right here. So what I'm looking for is the voltage between these 2 points, because the question is asking me to find the energy stored at the capacitor at t equals 0 minus. Even if it didn't ask me that, anytime you have a capacitor or an inductor problem, you need to find the voltage across the capacitor at 0 minus and the current through the inductor at 0 minus, because those are the things that control everything. So you need to find that. And so at 0 minus, this capacitor acts as an open circuit, and I made the bottom of the circuit ground, which meant that right above this 10 volt voltage source, I was at 10 volts. The capacitor is open, so I'm at 10 volts right here. And now if I look at this bottom part, this side, this is all ground. This is 0 volts. This is 0 volts. And so this is not here for all intents and purposes in terms of like if a current would flow. So if I wanted to see what kind of current was flowing through this, so if I make this point A and this point B, current is VA minus VB over the resistance in between them. And so my current would be my voltage here, which is 0, minus my voltage here, which is 0, over the resistance between them, which is 20 kiloohms. And so my current is just 0. So there's 0 current amps flowing through here. So that means that the voltage also does, there's no voltage change either, because there's no current flowing through these resistors. So it's just at 0 volts everywhere through here. And so in particular, it's at 0 volts right here. And so I have 0 volts here, 10 volts here. So the voltage from one side of my capacitor to the other is 10 volts. And then when I plug that into my formula for energy stored in a capacitor, I get U equals 1/2 CV squared. My V I found was 10 volts. So that was 1/2 times the capacitance was 100 nanofarads. That's 100 times 10 to the negative 9. So 0.5 times 100 times 10 to the negative 9 times 10 squared turns out to be 5 times 10 to the negative 6, which is 5 microjoules. And then I was asked the question, because one way I was thinking about this was saying, well, let me take this branch of the resistor, because this is kind of a weird looking circuit, and think about folding it over so that it's on the other side of my circuit, like this. And so I just took it from where it was and just folded it over. I can do that. Everything still has all the same connections. That's what's important. And now I can see, when I do that, that it is in parallel with a short. And so if any current comes here, it's not going to go through that resistor. It's going to go through the short. And so that's another way just to see that there's no current flowing through that resistor. So now I'm looking at t equals 0 plus. And at 0 plus, the capacitor is no longer an open circuit, but our switch has opened. And so now I have an open circuit down here at the bottom. But I did the same sort of thing because I want to see what my resistor is in parallel with. So my voltage source right here is now not connected to anything, so it's not going to play any role. But if I think about this 10 kilo ohm resistor right here, and where it's connected here and here. Or in other words, if it's connected here and here, it's in parallel with this resistor. And so, again, a physical way to think about it is folding it over, but its ends are connected here and here, so that makes it in parallel with this resistor, which was also 10 kiloohms. And this is 10 kiloohms. And this was 5 kiloohms. Now this was T equals 0 plus. One thing we know has to be true is that the voltage at 0 plus across a capacitor has to equal the voltage at 0 minus across the capacitor. So this was 0 and 10 at 0 minus. It's going to be 0 and 10 at 0 plus. So I have essentially this 10 kiloohms, 10 kiloohms, and this was at 10, this was at 0. This 10 kiloohms and 10 kiloohms in parallel, that would be equivalent to 5 kiloohms in one 5 kiloohm resistor. And so I know, and I'm looking for this current, I know by voltage division that if I have 0 at this side of these two resistors and 10 on this side, then in between it's going to be half. So I will have lost half of the voltage in between, so I have 5 volts right here. And so if I want to find the current flowing through this branch right here, IR will equal, I'll call this VA and this VB. IR will equal VA minus VB over 5 kiloohms, or IR will equal 0 minus 5 over 5 kiloohms, or IR equals minus 1 milliamp. I feel like I got positive 1 last time. Let's see. That's because I got these backwards. This was 10 and this was 0. This was 10 and that was 0. It doesn't change that this is 5, but it does change this to be 10. So 10 minus 5, so this becomes plus 1 milliamp. Yeah, this is 10 and this was 0 because it had to match what it was at 0 minus, and at 0 minus the top was 0 and the bottom was 10 on our capacitor. Okay, are there questions? So IR at 0 plus is 1 milliamp. Alright, so that was part B. Now part C says find IR of T for T greater than 0. So anytime you're finding a transient in a circuit that has an inductor or a capacitor, then whatever it is that you're looking for, in this case it's a current across a resistor, it'll be X at time T equals X at infinity plus X at 0 minus X at infinity times e to the minus t times 1 over tau, where tau is the time constant for whatever element it is that you have that is causing this transient response. In our example, we have this is a capacitor, and so tau equals RC. So now the next thing, so I'm going to find IR, so this is IR at t equals IR at infinity plus IR at 0 minus IR at infinity times e to the minus t times 1 over tau. Okay, so we have IR at 0. We found that to be 1 milliamp. Now IR at infinity, so let's take a look at our circuit at infinity. So we have narrowed our circuit down. We've said that this is what it looks like at 0 plus. So I'll just draw that again right here. So this is t greater than 0. Well, there's no source in there. And so eventually all of the power, all of the energy stored in this capacitor is going to dissipate. So at infinity, VC at infinity equals 0. All of the voltage it once had is going to go to 0. When this voltage goes to 0, the current will go to 0. And so if the current goes to 0, we have that IR at infinity is 0. Now we need to get RC. So RC is, R is the resistance, the Thevenin resistance from the point of view of the capacitor. And from the point of view of the capacitor, we've already done a lot of work on these resistors, but we can see that we have two 5 kilo ohm resistors in series. And so R Thevenin would be 10 kilo ohms. And so RC is 10 kilo ohms times our capacitance was 100 nanofarads. 100 times 10 to the negative 9 farads. So that is 10 times 1,000 is 10 to the third, times, that's 10 to the first, times 100 is 10 squared, times 10 to the negative 9. So it's minus 8 plus 5 is minus 3, so that's 10 to the minus 3, or 1 1,000th. So tau is 1 1,000th, or 1 over tau equals 1,000. So now I can plug into my formula, which was that IR of t equals IR at infinity plus IR at 0 minus IR at infinity e to the minus t times 1 over tau. So IR at infinity is 0. IR at 0 was 1 milliamp. At infinity it was 0. E to the 1 over tau was 1,000, so that'll be minus 1,000 t. So I can just write IR of t equals 1 e to the minus 1,000 t milliamps. So are there questions on that? Any step you need me to go back over? Nope. Okay, I'm going to stop this and save it, and then I'll start my next one.